like to welcome you to the Khronos workshop for hardware acceleration for machine learning computer vision through Khronos Standard APIs. So hardware acceleration.
Volume.
Volume. Are we good? Is this better? Good? Can you hear me okay? Is this better? Okay. So hardware acceleration is really what Khronos does. It's all these APIs, and this workshop is in particular APIs for machine learning and appropriate for the embedded vision workshop. The agenda for today, you can see here. So we'll have a couple of presentations here in the morning on, so there's actually 4 APIs that we're going to be covering from Khronos today. One is OpenCL, another is SYCL, OpenVX, and NNEF. NNEF is actually a file format, not an API, but we'll get to that later. And so first thing in the morning, we'll have a presentation from Neil Trevitt on Khronos in general and OpenCL. And then we'll go into a presentation on OpenCL and SYCL and how those are related. After a short break, we'll have a more in-depth presentation on SYCL. And then we'll move into some OpenVX presentations before lunch. So I'll give a short overview of OpenVX, and then we'll have a more in-depth presentation on case studies with OpenVX. And then we'll go to lunch. After lunch, there'll be more OpenVX presentation from AMD. And this is leading into, there'll be a hands-on portion in the afternoon. So there'll be a presentation from AMD on OpenVX and what they're doing with it, a presentation from AI Motive on NNEF, and then there'll be hands-ons for NNEF and OpenVX, where the NNEF hands-on actually leads into the hands-on for OpenVX. It's kind of a process flow that you'll be able to do. So that's the overall agenda. One question I have, so we want to make sure that we have, there's some internet access that would be required for the hands-on portion, and I wonder if I could get a show of hands of just how many people intend to stay for that hands-on portion, I guess starting from 2, running through the end of the day. Yeah, so it's I don't know, about probably 20, 30 people. Okay, all right, that's the overview, and I'd like to introduce Neil.
All right. Good morning, everyone. It's great to see such a good crowd. I hope you're going to find today interesting. We're going to go into much more depth than we had the chance to go into during the main sessions. So it's good to see you here. Please feel free to interrupt with questions. I think it's most valuable if we can make this more of an interactive session. It's a smaller room. So no, please raise your hand and shout if you have any questions as we go through any of the presentations today. Yes. Yes, all the slides, thank you for the question, excellent. All the slides will be posted up on the khronos.org website by probably this evening. Yeah, the videos will take a little longer, but we are doing this too. So, yeah, so you don't need to take pictures unless you want to, because the slides will all be available. So I was just going to spend just a couple minutes on Khronos in general, because involvement from the community and the industry is vital to any open standards organization. And then I was going to spend about 25 minutes just going through a little bit more detail on OpenCL, where we are today and where we're going in the near future in OpenCL's roadmap. So for those of you who haven't come across Khronos before, or maybe you've just heard about us at a high level, who are we? We are you. We are the industry. We're an open standards organization. We're open to any company that is interested to join. There are many different standard organizations throughout the industry. Each one has a particular focus, and we try not to overlap because life's too short. Our particular focus at Khronos is developing APIs to let applications tap into the power of accelerator silicon. And interesting accelerator silicon in the fields of 3D graphics, parallel computation, increasingly machine learning and inferencing, vision processing, obviously, here at the Vision Summit. And we are open to any company. We have about 150 members right now, everyone from Google and Apple and Intel all the way down to small startup companies with just 1 or 2 people. We're committed to developing standards that are freely available. There's no royalties to pay. We are intending to be a safe place for the industry to come and cooperate to create these standards for the good of the industry, but also for the good of the business of the members themselves. So we have about 12 or so active standards that are being evolved right now. We're focusing today on the right-hand side here, the APIs for parallel computation and vision and inferencing. But let's let you know if any of these other fields are interesting to you. We're not going to be covering them today, but there's lots of information on the website. 3D graphics, OpenCL, the original 3D API, and now the new generation Vulkan. Some file formats to go along with 3D, GLTF, which is getting a lot of traction for very efficient transmission of 3D scenes and models, and OpenXR for portable access to augmented reality and virtual reality HMDs. But today, as I say, we're focusing on, Frank said 4, I guess 5 if you count SPIR. We're going to spend a couple minutes on SPIR too, yes, but it's primarily the 4, 3 APIs and a file format. As I said, the engagement is really critical. Now, it's no use if the Khronos members are designing these standards with not getting engagement from the community that's going to be implementing them and using them. So we have multiple concentric circles of engagement, and we encourage people to get as close to the center of these circles as possible. Any company can join Khronos. There is a membership fee, but we try to keep it as small as possible. It's typically a few tens of K. That gives you access to all of the working groups, and it gives you a full vote and a voice in how these standards are evolved. If that's too much for you, then we do have advisory panels for some of the working groups, and that's free of charge, and it's by invite. But if you are active in the field and would like to contribute, please talk to us about becoming onto an advisory panel for the APIs that interest you. That lets, on an advisory panel, you come under the NDA and the IP framework. That lets us share draft specs with you and to have NDA IP conversations, so you can contribute as the specifications are being created. Outside the NDA, we're trying to put as much into open source. I'll talk about that, for example, what OpenCL is doing. Increasing the specs, the conformance tests, tools are all in open source, and of course anyone is welcome to come and help and contribute and comment there. And then last but not least, we have the forums and the Slack channels that are obviously open to anyone, and we do listen to the forums and the Slack channels. If you have input, please let us know there if that's good for you. So that's Khronos. Let me go into OpenCL. So there are a number of APIs for accessing accelerator hardware. A lot of them are specifically tuned towards GPUs. And I've mentioned OpenCL and Vulkan. There are other proprietary APIs now shipping in the new generation of APIs that's kind of started 2 or 3 years ago. There's DirectX 12 from Microsoft, Metal from Apple. There's CUDA from NVIDIA. But Vulkan is the new generation 3D API that is cross-platform and not proprietary to a specific platform. But they are just targeted at GPUs. If you have a system with heterogeneous hardware, maybe you want to bring in your multi-core CPUs into your compute offload, as well as a GPU, perhaps DSPs, perhaps some dedicated hardware, like an inferencing engine, or even FPGAs, then OpenCL is pretty much the only low-level API framework that gives you access to that diversity of heterogeneous processing elements in a single system. And we're finding that people are realizing that Moore's law is dead, meaning that the processors themselves are not going to keep speeding up in the way they've done before. And so the only way to get more performance for the latest applications is to use more processors, and increasingly more different types of processors, particularly in embedded applications like automotive. And so we're finding that the relevance of OpenCL to the embedded community is increasing over the last year or so. And that's why we thought it was worth giving you guys an update. So if you haven't used OpenCL, it is a low-level API. It is a foundational, we call it a foundational API. You can use it directly as a programmer, but it is low-level, and we'll go through the ecosystem. Increasingly, libraries and compilers and toolkits are based on top of OpenCL. So even if you're not using OpenCL directly, you might well be using OpenCL under the covers. So the idea behind OpenCL is to provide you complete access to what the hardware is doing. The OpenCL framework actually includes a couple of APIs, a platform layer API, so you can query what processors are in your system, and you can select them for your application and initialize them. And then a runtime API to actually download code into those processors and execute them and get the results back. How do you code those processors? We have what we call a kernel language. You can write, there's two, as a C variant and a C++ variant. So you write your actual kernels that you want to be accelerated and offloaded to your accelerator silicon in OpenCL or OpenCL C++. Then you use the APIs to compile those kernels, download them. You control what runs where the memory is allocated, how things are synchronized through time as your application progresses. So it gives you pretty good control over your compute resources and what you run on them. I'm not going to go into all the details here, but you can see that the first version of OpenCL was back in 2008, so OpenCL is over 10 years old. The later versions have been focusing on programmability. SPIR and SPIR-V are an intermediate representation that Khronos develops, and it gives us a lot more flexibility on the language front ends. I'll talk more about that in a second. The de facto baseline for all processors, pretty much, embedded processors and desktop processors, is OpenCL 1.2. There are vendors that ship the later versions, and FPGAs have everything they need in OpenCL 1.0. But 1.2 is the de facto baseline. Pretty much anyone other than FPGAs who's shipping OpenCL will be able to support at least OpenCL 1.2. Here's a little bit more detail. You can see kind of the waves of adoption, that the desktop adopted first, and then the mobile guys adopted the various versions, and then the embedded guys are beginning to adopt, and we want to drive that a lot more, and I'll talk about that in a second as well. And then the FPGAs vendors are supporting OpenCL, so it's quite a productive way of getting to your FPGA acceleration, but they only need OpenCL 1.0 at this point. So these circles are the first shipment from each vendor at that version, but there's a lot of strong activity kind of hidden here. So for example, since the last Embedded Vision Summit last year, Intel has refreshed OpenCL 2.1 for all of their current processors and their latest generation FPGAs. NVIDIA has refreshed, we are shipping 1.2. NVIDIA has refreshed that 1.2 though for the latest generation of GPUs, the Turing architecture GPUs, both on Windows and Linux. And the mobile guys, for example, Qualcomm, they are shipping 2.0 on their Adreno GPUs on Android. So there's a continual stream of new updates, so the latest silicon has up-to-date OpenCL drivers. We want to move, though, the adoption to the right. Obviously, the more people that support the latest versions, the better. There are some barriers to that, and we're going to talk about how we're going to hopefully solve that in just a second. So who's using OpenCL from the software point of view? a fun thing I've been tracking now for a couple of years, so I can draw a 3-point line for the first time. I track the number of open source projects on GitHub that are using OpenCL. It's not particularly statistically rigorous, but it is kind of a good indicator. And since 2017, EVS, we've jumped from just over 4,000 to just over 7,000. So it's a 70% increase in just 2 years. And the trend seems to be accelerating. There are a whole bunch of software packages out there that use OpenCL. The top box is desktop apps. Typically, it's video and imaging type apps use OpenCL to get to their CPUs and GPUs. There's lots of parallel computation languages and language frameworks that are built on top of OpenCL. Andrew's going to be talking about SYCL, which is a C++-based framework that is based over OpenCL. But there's JavaScript, there's Python, there's a whole bunch of stuff. There are lots of libraries, like linear algebra libraries, there's maths and physics libraries. But here at Embedded Vision Summit, probably the most relevant, a lot of the vision and imaging libraries are shipped with the option to have OpenCL acceleration. I mentioned it in my presentation in the main track, the OpenCV, for example, with their transparent API that shipped in OpenCV version 3, lets you offload OpenCL functions. OpenVX, which we'll be talking about at length later today, can now also use OpenVX both implicitly but also explicitly for hand-coded user kernels, and Frank will be talking more about that. And the big new trend, of course, is inferencing and machine learning. And as we were discussing in the main track, the two main ways of accelerating machine learning is to take your neural network graph and compile it into executable code, or to ingest your neural network into a pre-written inferencing engine. And both of those ways of accelerating inferencing make heavy use of OpenCL. 3 out of the 4, I'll say, big machine learning compilers, Glow, TVM, and PlatML, they all have the option of back-end OpenCL acceleration. And the trend is even more noticeable in the embedded space, embedded and mobile space. A lot of the embedded and mobile vendors, plus Intel and AMD, they're shipping inferencing engines. OpenVino from Intel, MIVisionX from AMD. ARM has the compute library. Huawei, which is still allowed to mention, right? Has Mace. Intel has CLDNN, Qualcomm, Synopsys, TI. All these guys have their inferencing engines. They're all based on the top of OpenCL. So even if you're not using it directly, again, OpenCL is pretty pervasive. So it's important that we make sure we take good care of this standard. It's being used quite pervasively in the industry. One of the things we're doing, from a logistical point of view, we've put the specs into open source. This means you can go and actually go to GitHub, find the actual ASCII doc resources that we use to create the formal specifications and the build scripts. And you can build your own version of the library. If you have, for example, a particular selection of extensions and you want to have an internal manual for your developers, you can mix and match and just have a manual that's just with the functionality that you want your programming team to use. The Conformance test suite is also available in open source. You can run the Conformance test suite on any implementation that you wish, keep everyone honest. But of course, the main point here is you can help us fix bugs and enhance both the tests and the documentation. If you keep hitting a bug in your favorite OpenCL implementation, suggest or even write a conformance test, and we can integrate it into the test suite so we can solve that problem at source. The way we've shipped OpenCL specs in the past is you have a different spec for each version. What we're working on right now, we should have it in the next few months, is we're actually bringing all of the versions of the spec into, we think, a much more manageable unified spec. So one spec that will have different carve-outs throughout the spec for the different functionality available in different versions. It's probably something we should have done a while ago, but it's the work is underway. As I say, there's a draft we've uploaded. Again, it's in GitHub, so let us know if you have any feedback. In terms of evolution, we're adopting a similar cycle to OpenGL and Vulkan, where we ship new functionality first as extensions, and then the extensions that get proven and adopted and receive thumbs up from the industry, we will integrate into the next core version of OpenCL. So some of the specs extension specs that we're working on include interop between OpenCL and Vulkan. Intel are proposing a scratchpad memory management extension, which we think will be really relevant to a whole class of embedded processors that want to have a more explicit management of local scratchpad memory, and some other functionality too. We're aiming at a new version of OpenCL, which we're just codenamed OpenCL Next. We're aiming for that to be released next year. And we're also looking at some things like Vulkan-like loaders and debug layers, and most importantly, flexible profile, which we think will make OpenCL a lot more relevant and easier to ship for the embedded processor community. So let me talk about that just a second. I think OpenCL, we've kind of belatedly realized that we have too much heritage from our HPC and desktop roots. That's kind of where we started. And we find that a lot of the embedded DSP and increasingly inferencing engine type of processors are wanting to use, and in fact they are using the OpenCL framework. They just can't call themselves Conformant OpenCL because they don't have all of the functionality in the current big monolithic OpenCL spec. The most obvious example is currently even OpenCL 1.2 requires you to have 32-bit floating point, which is often very useful, but there are many markets where it's not relevant, and you find lower-end processors that don't want to ship 32-bit floating point. For vision and inferencing, you just don't need it. And it's too much busy work to emulate it in software. No one's ever going to use it just to be conformant, so people don't do it. So we want to be able to slice and dice the OpenCL spec and let embedded processor vendors ship just the functionality that's relevant to their market and their customers. So we're working busily right now on this concept of features. We're deciding which parts of the current monolithic spec we can define as a feature, and we can make those optional, and you can leave out those features if they're not relevant to your market and still call yourself conformant. And you might imagine there's quite a spirited debate as to what those features should be. The danger of these features, though, of course, is fragmentation. If we're not very careful, every OpenCL hardware vendor is going to ship a completely different set of features, and your portability across different vendors will be damaged. That's definitely a danger we're very aware of. We're trying to mitigate that through feature sets, which is a set of features that we can define for a particular market that must be present if you want to claim conformance to that feature set. So, for example, we might well define a feature set for embedded vision and imaging. And we would enable people to be conformant to that feature set. So we would expect anyone shipping OpenCL for vision and imaging would have those features. They can have more features as well if they wish, but that will provide the portability that OpenCL currently provides with a lot more flexibility. So to say, we're having a lot of discussions about the feature sets. We'll have feature sets probably that draw the line around current spec versions, so an OpenCL 1.2, an OpenCL 2.0 feature set. We might define a feature set of the OpenCL functionality that runs well over Vulkan, a Vulkan runtime. That is interesting to some people. But it is actually interesting. A lot of the vendors do care about having a common feature set, so you can go from one DSP vendor to another DSP vendor without making any code changes. But we have also recognized in the embedded space there are vertical markets. Very often the same company will be writing the drivers and the libraries and the applications, they still want to use OpenCL because all of the benefit, they don't have to reinvent everything, all the tools are there, the programmer's expertise, they don't have to retrain people. But they will never have to take those apps from one vendor over to another. So for example, NVIDIA, we are fully integrated in our automotive stack. We don't expect to ever have to take our automotive apps and run it on another vendor's silicon. In that kind of market, feature sets maybe aren't so important. And it's actually more important to reduce the surface area of the API, particularly in safety critical systems where every line of code is costing you, significantly in terms of certification. So for that kind of market, perhaps we will just enable an implementer just to draw a line exactly around the functionality that they need to ship for their own stack and still call themselves conformant. They just won't be conformant to any of the feature sets. So anyway, it's an ongoing discussion. If this is kind of interesting to you and perhaps relevant to your company, again, please consider joining and getting involved. We definitely welcome your input. I want to talk a little bit about tooling and languages. We have a subgroup inside the OpenCL working group that's working to bring a lot more rich programming capability to OpenCL. And one of the key ways of doing that is not to reinvent everything ourselves, but to work much more closely with the established compiler community, primarily LLVM, which includes the Clang front end. So we now have a number of active source projects that are leveraging and upstreaming into LLVM. We want to make our intermediate representation, SPIR-V, a first-class LLVM intermediate representation. We're extending the translator between SPIR-V and the LLVM intermediate representation. We're making sure the libraries for OpenCL can work well with the Clang front end. So there's a lot of work that's ongoing. And probably the most important one is what we're calling C++ for OpenCL in Clang. It's a snappy name, but it's quite descriptive. And it's potentially confusing. This is different to OpenCL C++. OpenCL C++ is the specification from Khronos that defines the C++ kernel language as a ratified spec. And that's awesome, but we're finding that the community is much more interested in accessing a kernel language that is in open source and can be evolved much faster in an open source way. And this is exactly what C++ for OpenCL in Clang is. So we're taking the Clang front end, we're already extending it to include OpenCL C capabilities, and then we're mixing in C++ 17 capabilities too. So if you are already writing OpenCL C kernels, you can use this front end, and you can begin to mix in incrementally some of your C++ code if you wish to. The reason we can do this is because we have SPIR-V, this intermediate representation. And let me explain how that works. So this is the current OpenCL compilation flow. It's the primary line across the top. OpenCL has a number of interfaces for ingesting code. You can take in an OpenCL C source file, and the green box is a front-end compiler, and that ships with the driver, because you can throw an OpenCL C source file at an OpenCL runtime, and it will get compiled for you into probably an intermediate proprietary intermediate representation and into a backend to create the device binary. You can go through SPIR-V at any time, but it's optional. But the key thing is the front-end compiler for OpenCL C ships with the driver. So if we want to add new language capabilities to, for example, OpenCL C, everyone has to update their drivers. And that may take some time. That's definitely a friction point in the ecosystem. Now we have SPIR-V, this intermediate representation. We can split the language front end from the driver back end. So you can have an offline compiler that does the front end compilation. It can generate a SPIR-V file, and then the driver only has to ingest SPIR-V, not OpenCLC. And the expressive power of SPIR-V is enough that we can do quite a lot of language innovation without having to update the SPIR-V version. So, for example, we can put in things like variadic macros, atomic functions, even templates are possible with the current drivers that are currently shipping out there. So we can let the front-end compiler evolve at open source speeds and feed that into existing drivers that are shipping on everyone's hardware. We're getting quite positive feedback that this is a much better way for the community to go. But to be clear, we're not removing OpenCLC ingestion. That will remain, because a lot of applications obviously rely on that. But this is kind of similar to the extension mechanism I was mentioning before. We can try out a lot of these language features in open source, and the ones that get interest from the community, we can consider a driver update on a much more considered timescale. So I've mentioned SPIR-V a few times. It often gets forgotten, but in many ways it is actually, in my opinion, one of the most important standards that Khronos creates, because it does have this effect of enabling separate innovation in the language front ends from the hardware drivers. SPIR started with OpenCL, and then Vulkan came on board, and then we have now a common format that we share between Vulkan, OpenCL, and OpenGL. It's called SPIR-V. The V stands for Vulkan. And we have now an increasingly rich ecosystem of tools. There's cross-compilers, there's disassemblers, there's optimizers. There are the shading language front ends for Vulkan, GLSL, and HLSL. HLSL has two compilers. We recommend people going through DXC. That's actually the Microsoft front end that we're upstreaming to. But for OpenCL, now we have this range of language front ends for your kernels that are feeding into SPIR-V, sometimes directly, sometimes through LLVM. One interesting wrinkle here is one little box I want to highlight, CLSPV. OpenCL has had a checkered history in terms of support from the big platform vendors. For example, Google has never supported OpenCL as part of the Android platform definition. And they have valid reasons for that. But it makes it interesting in terms of OpenCL adoption and momentum overall. Lots of the chip vendors do ship an OpenCL on Android, but they keep it under the covers for their inferencing engines and compilers. They don't expose it to end user programmers. But there are, of course, a lot of people that are investing in OpenCL code would like more flexibility on where they ship that OpenCL code. And so we have a number of projects underway to enable OpenCL code to be deployed where there aren't native OpenCL drivers. One good example, and it is relevant to my example, which is Android. It would be kind of cool to be able to take your existing OpenCL kernel code and API code and run it on Android, for example. And Android has Vulkan. So running your OpenCL code on top of a Vulkan runtime is commercially relevant to an increasing number of OpenCL developers. The first developer that worked with Google on this open source CLSPV compiler was Adobe. Turns out Adobe have 200,000 lines of OpenCLC production code for their video editing applications. They are now using successfully the CLSPV front-end compiler to compile that code to the Vulkan version of SPIR-V and successfully running it on Android. We now have Sony, and both these developers have agreed that we can say all of this. Sony is now working with Google, the second in the queue, and turns out they have 355 quite complex compute kernels in 75 files, and on just passing it through, first pass, 40 out of the 75 worked. So CLSPV is definitely an experimental compiler. We're nowhere near being production, but we're already getting quite good results. We need more developers to try their kernels through the CLSPV compiler so we can make it less monoculture and more robust for more different kernel types. Kevin Petit from ARM has also put CLOVK into open source, which is an API translator, which is an interesting addition. For most people, it is the kernels that's the major code investment, so if you can bring those over. So this is the project flow we're using for CLSPV. We're increasingly trying more and more kernels, real kernels, and we're about to go out into the open source libraries and try some of the kernels there. If we find that there are gaps in the compiler itself, we can fix them. We may need to do updates to do a better mapping. There may be holes in Vulkan, because OpenCL has a lot fuller compute capability than Vulkan right now. But this is a very data-driven way of persuading Vulkan to adopt some more compute functionality into their runtime. We can go with real data saying, look, we have ISVs, we've tried our best to map onto Vulkan, but here's where the gaps are. Please help us fix it. And we can go into the Vulkan working group and have that discussion. And I think my last slide here is, I don't know how relevant this is to folks using OpenCL. It's kind of ironic. Apple were the main instigator for OpenCL back over 10 years ago. But now they've announced they're deprecating OpenCL because they're focusing everything on Metal. They only have GPUs, so they only care about GPU APIs, I guess. And they want to stonewall themselves off from the rest of the industry. But that gives an interesting dilemma to people that are using OpenCL, and part of their deployment strategy is on Apple platforms. So we're thinking of, and this isn't started yet. This is actually a call for interest. If you're interested in this, this is an embedded conference, so maybe Apple isn't so important. But if you are interested in this, let me know. We'd love to kind of get a community together. It's quite feasible to use a lot of the open source tooling infrastructure around SPIR-V to imagine a OpenCL over Metal, just like CLSPV is OpenCL over Vulkan. Actually, Metal is a lot closer to OpenCL than Vulkan. The mapping would actually be a lot easier for OpenCL over Metal. We already have a lot of the front ends and cross translators in place. This may not be a very big project, and may be of interest to some people out there. Please let us know. So I think that's it for me. Hopefully that was interesting. Let me pause. Any questions on OpenCL before we go on to the next API? Stunned you all into silence. Yeah.
I'd like to comment on the fact that you're actually from NVIDIA, and so OpenCL and CUDA are not like how you deal with the government.
I'm schizophrenic. No, but seriously, the NVIDIA is fully supportive of OpenCL. I know we don't support 2.0, which is a pain for many folks, but our support for 1.2 is committed and strong. We have a full driver team. We're doing bug fixes, performance optimizations, reporting it to the new generation GPUs. So now our 1.2 is solid and will continue forever. We think the 2.0 transition has been difficult, and there are some poison pills in 2.0 for NVIDIA, which is why we haven't taken that step, which is why we think the flexible profile will actually let us move the wavefront forward. So we're actually quite looking forward to working with OpenCL next. Yeah.
Raspberry Pi, very popular platform to set lists, right? Especially if you want to start. Can you use the microphone?
Yeah, did you?
You have OpenCL for Raspberry Pi? Oh, I'm sorry.
Do we have a mic? Can we use the lapel? Oh, there's one there.
Yeah.
Oh, there's one here. There's two. Sorry.
Longer than the question. Yeah, so I'll make, hello, can you hear me?
Wait. We're debugging the room, just a moment.
Apparently, this mic doesn't support OpenCL.
Can you hear me now? Yeah, all right. So anyway, so I was talking about Raspberry Pi, right? So Raspberry Pi is a very popular platform, especially if you want to prototype something real quick, right? Like myself, for example, like when I try something real quick, Raspberry Pi is a great platform to do that,
Yes.
okay? But there is no OpenCL for that.
Actually,
Why is that?
Actually, there is.
There is, I couldn't find it.
I know, we couldn't find it either. But the good news is, Frank will be talking about this, we're actually putting an OpenVX on Raspberry Pi for exactly the good reasons you say. And we have actually located an OpenCL, and we're going to be using that OpenCL in our OpenVX project. So now we've found it, we're going to be promoting it. I mean, Frank, who created that OpenCL, do you know? Independent vendor. So, but there is an OpenCL implementation, and we'll be publicizing more details around that because it is interesting.
Can you tell me approximately the time frame for that, when I could get my hands on it?
In the next months. Cool. Well, thank you, everyone. And let me hand over to Andrew, who's going to be talking about SQL. And I have